All right, thanks. And thanks for inviting me. It's my pleasure to give a talk here. So today I want to talk about this topic called correlation clustering. And then this is joint work with a lot of people, Nairen, Vincent, Shi, Alantha, and Lukas. And then let me get started. Okay, so yeah, this is like very like some simple combinatorial optimization problem. So let me jump directly into the definition of the problem. If my clicker works. Okay. Then okay. Good. Okay, so that's the definition of the problem. Okay, so input is simply a one complete graph G, and then each edge has either labeled a plus or a minus. Okay, let's say like E plus is a set of plus edges and E minus is a set of edges. And then throughout this talk, I'm going to use a color red to denote plus edges. And then I'm going to use a blue color to denote the minus edges. So that's your entire input, just like each complete graph divided into like plus edges and minus edges. Here, my goal is to partition the vertex set into like V1 through Vk. Okay, just like the partition the cluster, the V into like V1 through Vk. And then one noticeable part is that the K is not part of input. Okay, so algorithm can choose whatever K it wants. K can be 1, K can be n. Yeah, that's a cool thing about this problem. And then objective function is to minimize the number of minus edges in the same cluster plus the number of plus edges in different clusters. Okay, so intended meaning is that if the edge is plus edge, so then it means that this edge wants two of its endpoints to be in the same cluster, like plus, like same cluster. Okay, so if you put them into different clusters, then you gotta pay one because like you are violating that edge. Or if you look at the minus edge, then obviously this guy wants these two endpoints to be in different clusters. So if you violate that, then you gotta pay one. Okay, so it's a minimization problem. So you want to minimize the number of mistakes. Okay, so that's yeah, very simple problem. That's the entire description of the problem. Any question? It's good. Good. So then yeah, one can see that if you look at this solution, then this is a perfect solution because every like intra-cluster edges are like plus edges, good edges, and then every inter-cluster edges are like minus edges. Okay, so we are making no mistakes, so objective function is 0. And then if you look at this solution, then one can see that we are violating 2 plus edges, so objective function is 2. Okay, so that we are simply trying to minimize the number of mistakes. Okay, so then yeah, how do you study this problem? Okay, it's a clustering problem, so hopefully it's applicable. But then compared to other like clustering problems well known in the theory literature, like say K median, K means. So then one nice thing is that we don't need K in advance. The algorithm can choose whatever it fits. And then compared to all these problems, we don't need an ambient metric space. Okay, so this problem is well defined, even when the plus minus patterns are arbitrary, and then indeed it's the focus of the problem to find the clustering that is consistent with the given data. So like one kind of a concrete application is building the following entity graph on the web. Okay, suppose that yeah, you are going to internet and there are many pages on Michael Jordan. Okay, so IMDb has like 2 pages for Michael Jordan, Wikipedia has 3, and the DBLT has 1. And so there are like 6 pages referring to Michael Jordan. But then yeah, one can say, okay, so some of the pages are referred to the same person, and then some other pages are referred to different Michael Jordans. Okay, so then yeah, how can you cluster them so that like each cluster corresponds to different pages of the same person? Okay, so then one way to solve the problem is to run a pairwise classifier within each pair. Hopefully it's gonna give you some information about like, oh, like these 2 pages are the same person, these 2 pages are different people. And then yeah, once you get this data, then one can use our correlation clustering algorithm to correctly figure out the clusters that correspond to like different people. Okay, so this is one example. And then similarly, another example is clustering images after Googling my name. Then yeah, one can see that all the edges are like plus edges, and then there's only one cluster in the optimal solution. And then yeah, more like the worldly secular motivation is that actually this is some problem that like people in practice or at least the outside theory cares about. Okay, so one can see that this is by pulling Nikhil Bansal's like most cited paper by a factor of 4. Okay, so this box paper is cited like 1,800 times, which means that someone outside theory cares about that. And then even like yeah, even I can tell you from my personal experience that this industry people care about it because I have only one serious industry experience, which was like summer internship right before my PhD. And then there somehow I was like, my only job was to improve their like correlation clustering algorithm. So they were actually running some correlation clustering algorithm. Okay, so yeah, if your condition mean on being me, then actually correlation clustering is 100% what's going on in this tree. Okay, so yeah, so there are all good things about this problem. But then let's so what's the history of this problem? Okay, so this is the first related by this work by Banzal, Blum, and Chawla, and then original work already gave an one approximation, which is nice. But then somehow people cared about improving approximation ratios for this problem. Okay, so then one can see that it was improved into the 4 quite soon after, like 3, 2.5, 2.06. So there was a state of art until a couple of years ago. So 2.06, that's good. But then from the lower bound side, okay, so people knew that, okay, 1.0001 is impossible. And then probably more importantly, people somehow thought that like 2 might be the barrier of this problem. Because if you look at the standard LP of this, the LP relaxation of this problem, then it has an integrality gap over 2. Okay, so, and then people couldn't go beyond, people even couldn't match 2, even today. Okay, so the 2 was I thought as a barrier. And then yeah, we overcame it. But then yeah, before going into our results, actually I wanted to mention that, okay, so our version is nice. But then if you look at the correlation clustering, you can think about other versions. Okay, so why should we talk about complete graphs? Okay, so what happens when the graph is not complete graph, just like any general graph? Okay, that's one generalization of the problem. And then you can also think about different objective function. Okay, so what about maximizing number of satisfied edges instead of minimizing number of wrong edges? Okay, that's a valid thing. So then yeah, you have like 4 versions. This one is our version, but then you can think about all the other 3 versions. And then yeah, people thought about all these like 4 versions, and then including the Swang's work for general graph maximization problem. But then the reason that I like this problem, or like many people like this version more, is that somehow like one can see that very soon after the original paper, people kind of realize, okay, like the other versions are kind of equivalent or like very similar to the problems that we already understand. Okay, so for example, this version, the mean version in general graph, I think people quickly realize it's equivalent to multi-cut. And then this version, I think people, okay, so it's kind of related to max cut, not exactly. So we can use like the SP rounding technique. Whereas our version, okay, so our version, I think one nice thing about this problem is that this is the problem where like people develop new techniques, which is used for other problems. And then hopefully, I think I hope that that's the case for our techniques as well. Okay, so that's yeah, why we are focusing on this problem. But then yeah, of course, all the other problems are almost exactly understood. Okay, and then going back to our result. Okay, so then yeah, what we did is that in the past 2 years, we had a series of papers, and then the most latest one gives you like 1.4 something approximation algorithm. Not quite. So 1 plus 437 plus epsilon approximation algorithm in time n to the poly 1 epsilon. Okay, so in reality, running time can be quite high if you want to beat the approximation. But then anyway, that's what we did. And then from the hardness side, I think on 24/23, we got the NP hardness. Though I think I'm going to mention later, but then like 4/3 is like actually natural barrier for our approach. Okay, so so then in that sense, then the upper bound 1.43 is not very too far from like 4/3, the natural lower bound that I will describe. And then of course it's a series of 3 papers, but then I will mainly present the algorithm from the latest version, which already has all the ingredients from the previous versions, probably like packaged differently. Okay, so for example, I think the one central object of this talk will be this thing called the cluster LP. Okay, so it's again a gigantic LP that has an exponential number of variables, and then solving that LP is actually the most technical part of this paper. And then somehow in the previous version, so the algorithm to solve the cluster LP in this version was an actually rounding algorithm for the previous version. So like, yeah, then we're gonna see this, but then at least that's how we just move around the things. Okay, so yeah, but then yeah, let me get to the cluster LP in the next slide, but then let me just like first show you what the standard LP was. Okay, so standard LP was like very natural. So for each pair of vertices I and j, you're gonna have a variable xij. And then the intended meaning is that, okay, so if I and j are in the same cluster in the optimal solution, okay, so then I want xij to be 0. And then otherwise, if they are separate, then I want xij to be 1. That's my intended meaning. Then yeah, one can see that, okay, so if in that case, the edge ij becomes 1, if ij is separated, xij is 1, but ij is plus edge. Okay, so then because it means that ij is plus edge, but then we separate them. Or if ij is a minus, then we want xij to be 1. So you're gonna pay 1 if xij is 0. Okay, so, and then of course, then fractionally one can think of this as some kind of distance. Because we can put triangle inequality, saying that if ij are together, if jr are together, then ik must be together. Okay, so that's that's the whole idea, and then that's the whole LP relaxation of this problem. Okay, so every xij must be between 0 and 1, and then you should have a triangle inequality constraint, and then objective functions are exactly this. Okay, you're paying xij for plus edges, you're paying 1 minus xij's for minus edges. Yeah, so that's a very natural standard LP. And then that guy has an integrality gap at least 2, and then at most 2.06. Okay, so it's still open that integrality gap of this guy is exactly 2 or like strictly greater than 2. I think it's a still very interesting open question because like still our like new algorithm will use like some ideas from the old rounding algorithm. Okay, so if you give me how to like get to approximation algorithm with respect to this LP, then it might actually improve our like even new algorithm further. Okay, so that's a standard LP. That feels good. Yes. Yes. Good. That's a standard LP. But then here's our cluster LP. Okay, so it's a much larger LP. It's gonna have like 2 to the n variables, 1 for each subset of vertices. Okay, so for each subset S, I'm gonna create this variable called the Z sub S. And then it's a intended meaning of Z sub S. Okay, so I want Z sub S to be 1 if S is exactly 1 cluster in the optimal solution. Okay, so it's not a subset of a cluster or a superset of a cluster. Okay, if it's exactly 1 cluster, then I'm gonna set ZS to be 1. Okay, so then, if that's the meaning, then at least this constraint is clear. Okay, so yeah, for each vertex I, it should belong to exactly 1 cluster. Okay, so summation over S including I, this sub S should be exactly 1. Okay, so that's a natural constraint. And then one can also put one can also infer xij variables from Z variables. I was saying that okay, so when I and j are together. Okay, so I and j are together if and only if there's like a cluster that contains both I and j whose ZS value is 1. Okay, yeah, if you think about the more probabilistic way, then the ZS is like the probability that S is exactly 1 cluster in the optimal solution. Okay, so then xij is gonna be like 1 minus the summation over S including ij Z sub S. Okay, so that's yeah, so and then that's the entire like cluster LP. Okay, so I think I'm gonna take a pause. Like, any question? Because like that's the really central objective of this. Yes. Good. Okay, so then yeah, this is the object that we can still a relaxation, and then yeah, our goal is to use this LP to solve to a better approximation algorithm for a clustering correlation clustering problem. Okay, so then yeah, given this LP, then the whole like paper is divided into 2 parts. Okay, so the first part is to solve this LP, and then actually if you go back to this LP, and then if you are approximation algorithm person, then you can kind of see like this thing kind of looks like this thing called the configuration LP. Okay, it's like you are like looking at every possibility for like 1 variable. And then you are like putting some consistent constraints there. And then if you're familiar with configuration LP, then their like typical way to solve it is to take a dual and then solve the dual problem exactly, which will give you a separation oracle and blah blah. But then I think this approach is not at least like naively working for this LP, because if you take a dual, then actually you're gonna get some kind of Sparse-Scar problem, which is NPR, at least in general graphs. So we need to use the fact that we are dealing with a complete graph as an instance. And then we need some new machinery to separate the dual LP. Though I think we are not going through like dual, we are just like directly solving the this LP. Okay, just wanted to mention that. But anyway, so then of course, like the first part of the paper is to solve this LP. Of course, we're not gonna exactly solve it, but then we're gonna compute the 1 plus epsilon approximation for this LP in time n to the polynomial epsilon. Okay, actually that's probably more technically involved part of the paper. But then of course, second part is around this LP by only losing 1.4 factor. Okay, so but then let's go to the part 1 first. And then as you can see, at least the one typical or like the key ingredient that we are going to use is this thing called the variance reduction using Sherali-Adams or sum of squares. That was known in the TCS literature for many, many years, at least like 10 years. So I'm gonna start with that. But then once you are trying to use that, then you're gonna see some problem that happens for like the correlation clustering. Okay, so then we're gonna see that bottleneck, and then we're gonna see how we can overcome this bottleneck by using the first notion called the preclusering. Okay, let's talk about how to solve it. Okay, so then if you kind of know me, then I come from this constraint satisfaction problem literature. Okay, so when I see a new problem, I view everything as a CSP. But then correlation clustering, it's a much easier job. It's already kind of CSP in some sense. Okay, so I'm gonna say that this correlation clustering instance that we saw is exactly an instance of CSP, where we have each variable for each vertex, and then the alphabet set of values that a variable can take is exactly like n. Okay, because one value corresponds to one cluster, and then there can be n most n clusters, or we can say the alphabet size is n. Then of course, like each edge becomes a constraint. Okay, so if you have a plus edge, then this plus edge demands that okay, the both values, I and j values, must be the same. Okay, if so, that's satisfied. Otherwise, it's unsatisfied. And then of course, like the minus edge ij will require that ij will get different values. Okay, so plus edge is like the equality constraint, and then minus edge is an inequality constraint. Then the goal is to find an assignment to maximize the number of unsatisfied constraints. Okay, so then I didn't do anything. I just like stated the exact correlation clustering problem in a different language. It's just like CSP. That's good. But then if you think about CSP, then you probably think about the problems called the max cut, max set, max lean, these guys. Okay, so then and then you can see like some kind of a similarity in the dissimilarity between this problem and the more famous problems. Okay, so what are those like differences? Okay, so compared to the usual max CSP, there are like several differences. Good difference and then bad differences. Good difference is that the instance is a complete graph. Okay, that's good. At least we are like significantly restricting our instance to the complete graphs. That's good news. But then prospect bad news is the alphabet size is n. Okay, so like max cut, like max 3 set, the alphabet size is 2, true or false. Now it's n, so probably it's gonna get it's gonna make things more harder. And then when it looks really benign, but then actually like probably the bigger problem is that my objective function is the number of unsatisfied constraints. It's a mean problem instead of max problem. It looks benign problem because like in the exact optimizations they're the same thing. But then if you care about approximation ratio, then actually one can say this is probably the bigger problem than having the large alphabet size. Okay, so let's try to see at least why by at least trying to use the complete graph structure. Yeah, because at least the complete graph is it's a nice news. And then if you ignore these other differences, so if you think about the max CSP, the say like Boolean alphabet case, like constant alphabet case, so then this is something that people studied a lot for the last like 20, 30 years. And then you have this nice result, say that every, not just any specific CSP, but every max CSP, 2 CSP, meaning that each constraint depends on 2 variables, on dense graphs admits p-test. Okay, so it doesn't matter, it's a max cut or like max lean, max 2 set, it doesn't matter. So every 2 CSP on dense graph admits p-test. Okay, so that's really good news. Okay, so it's even more general than complete graphs. And then people use these ideas to extend the result to like other class of graphs, even more general than dense graphs, including expanders, low threshold rank graphs, like more special notions of dense graphs. And then what I like about this technique even more is that if you look at the literature, then there are like three seemingly independent, at least to me, equally beautiful techniques. Okay, so there is a technique using random sampling to get p-test. There's some version of regularity lemmas to get p-test, and then there's also the technique called technique using convex hierarchies, some of scares or Sherali-Adams to get p-test. Okay, so I mean there are like, of course there are some connections, but then at least I think there are like more to discover. Yeah, so that's what I like about this the result and techniques. And then in hindsight, actually the original paper even started even gave a p-test for the max version of correlation clustering using one of these ideas. Okay, so yeah, so the upshot is that dense graph is good if you ignore the difference between max and mean, and then if you just ignore the difference between the alphabet size. Okay, that's good. And then we want to use it. Okay, but then let me just like briefly tell you how to do this using Sherali. So it's not part of the paper. Then let me just give you some idea. Okay, suppose that we are trying to solve max cut in a graph with the n-square edges, so that dense graph. Okay, so then of course we are going to use like some notion of Sherali-Adams. Okay, so for me it's nothing but some kind of LP, some strengthened version of LP. But then what we do is that for any subset variable that has at most r vertices, and then suppose that the alpha is this partial assignment to the variables of S. Okay, so then for any like the pair of S and alpha, I'm gonna create a variable X sub S alpha, whose intended meaning is the probability that S is gets some assignments alpha in the optimal solution. If opt is probability distribution over like optimal solutions. Okay, so that's my intended meaning of X sub S alpha. Okay, so then one can see that number of variables will be roughly n to the r. And then, of course, if you have this interpretation, then one can naturally put some kind of consistency constraints between these variables. And then the rounding algorithm is also very simple. So the way we do it is that we sample set of vertices T that has r minus one vertices, uniformly random. And then we sample alpha from T's local distribution. Okay, so you choose like the r minus one variables locally, randomly, and then you have r minus one variables, and then you look at their local distribution, and then you sample alpha assignments for these T guys. Of course, then we need to decide the assignments for all the other variables. But then what we do is that for any variable I outside T, we're going to sample I's value conditioned on the T getting alpha. Okay, so I can do this because I do all these I's separately. And then for each I, at least I'm looking at the R local distribution. Okay, so I have a local distribution for T union I. Okay, so given T, I can sample I conditioned on T being alpha. Okay, so that's roughly, I mean, actually that's something that's the entire algorithm. And then we're not gonna prove how to do it, how it works, but then at least so this was done in 2011 and around that. And then these analyses show that if you do this rounding, so then the value of the max cut that you get, this rounding, will be close to the value that LP gives you, which is good news. But then there is this additive error with epsilon times n square, where like epsilon is the 1 over square root of r. Okay, so then as you increase r, then actually at least one can make sure that epsilon is like small enough constant. But then your error is like epsilon times n square. Okay, so for dense graph, and then if your objective function is max, then you're fine because like then you know that okay, so you anyway have like n square edges, and then you know that your optimal value is greater than like half of the edges. Okay, so then as you like decrease epsilon to an arbitrary small constant, then epsilon n square additive error is not a big deal. But then if you talk about the minimization problem, then even the additive error 1 is a devastating, because like if optimal value is 0, then you want to find a solution of value 0. Okay, so getting any additive error, let alone epsilon times n square, is not gonna do anything for our situation. Okay, so it's it's kind of like stupid, but then it's a bottleneck, and then it's a real bottleneck we have to overcome if you want to say anything about the minimization problem. And then I still like this tool. So I will use this tool as a black box in some sense. Okay, so then here like comes the notion of preclustering. Okay, so like the idea is really simple. So I think, okay, so if I use this like the fancy rounding to the whole instance, so then I'm gonna get an additive error like whose amount is proportional to the my instance size. So then my idea was, okay, let's kind of like partially solve the problem first. Because let's fix the obvious part of the solution, such that the remaining part of the solution is not too much. And then so for the remaining part of the problem, then we're gonna apply this like the fancy rounding. But then in that case, like the additive error should be proportional to the size of the remaining instance. And then if we can bound that guy by opt, then we're gonna be fine. Okay, so that's some very like a natural idea. And then that's what we did. Okay, so we gave a like separate combinatorial pre-processing algorithm that partitions each pair into like 3 categories. Okay, so, E same, E different, E question mark. Okay, so E same means that okay, the pair we already decide them to be the same cluster. Okay, that's good. And then E different, we already decided okay, so these 2 Ys like they will be it's a separate cluster for sure. And then of course it's question we don't know yet. We gotta do fancier things to decide the fate of these guys. Okay, so that's all. We just partition B choose 2 into like 3 categories, and then there exists a near optimal solution, 1 plus epsilon approximate solution that is consistent with our decision. Okay, so we basically partially solve this problem, while leaving at most like order opt number of still like undecided pairs. Is this statement clear? Okay, so the proof, it's quite clever, but then it's 2 pages of natural combinatorial algorithm argument. Yes, I prepared something, but then let me just skip it for the sake of time. Okay, so then we did the pre-clustering. So we made some decisions, and then the number of question marks is at most like order opt. And then we are still trying to solve the cluster LP. But then still we gotta have like start from somewhere. That's where this our relaxation comes. And then it looks a lot like this Sherali-Adams or like some scarce relaxation with some more like strengthening because of the correlation clustering problem. Okay, the fix any constant R. So R is gonna be like number of rounds in some sense again. And then let's say that S1 through SL are disjoint sets of vertices, and then their union sign is at most R. Okay, that's good. But then I'm gonna have this the L numbers again, L numbers as well, S1 prime through SL prime. Okay, so these are all these guys. And then given S1 through SL and S1 prime through SL prime, I'm gonna create like this one variable called Y sub S1 S1 prime bar S2 S2 prime bar all the way through SL prime. So that's one variable. Okay, so then what is my intended meaning of this variable? So I want that, of course, the S is like some set of vertices that has the R vertices, and then of course like there must be optimal solution which partitions the whole vertices into several parts. Okay, which means that optimal solution will partition S into like several parts as well. Okay, so first thing I want is that if you look at how S is a partition with respect to the optimal solution, so then the induced partition by S should be S1, S2 through SL. Okay, so the optimal solution partitions S into L different parts, and then each part is S1, S2 through SL. That's my first requirement. But then of course I want slightly more information because okay, so then I know that okay, within S, S1 is one part induced by optimal solution. But then I still want to know, okay, so then S1 is like the part of optimal solution, but then there are like other vertices in that part outside S. Okay, so then I want to know the size of that part as well. Okay, so the second condition is for every I. So Si is in a cluster of size Si prime, including all the vertices of not in S. Okay, so there was multiple. So let me give you a quick example. Suppose that this is the optimal solution, which partitions like vertices into 4 parts. And then suppose that S is a ABCD. These are 4 vertices. Okay, so then one can see that S is a partition to 3 parts. Okay, so the A is in own part, B and CD. So like optimal solution partitions S into 3 parts. And then if you look at the size of each part, okay, so then the part containing A has like the 2 vertices total, and then part containing B has like 2 vertices total. Part containing CD has like 4 vertices total. Okay, so then the variable that will be set 1, the actually true variable here, is going to be Y sub A2. A is its own cluster that has size 2, and then B2. B is in a different cluster that has size 2, and then CD 4. Okay, so that's my intended meaning of this variable. Okay, so any questions about this the variable definition? Okay, just just basically tell me like everything that's going on in S. How S is partitioned, and then in the bigger picture, how large is their clusters. Okay, so that's my that's my variables. Then of course I'm not gonna even write them down, but at least one can see some kind of consistency between these 2 variables. Okay, so if S is a subset of T, then we can naturally require that whatever was going on for T, the configuration of T, must be an extension of a configuration of S. Okay, for example, if you just look at S being A, B, C, D as before, and then T is like A, B, C, D, E, like this. Okay, so then for S, we kind of saw that, okay, so then for S, the right choice was like A2, B2, and then CD4. And then for T, in this case, like E belongs to the cluster of CD that has size 4. Okay, so then in this case, the thing going for T is the A2, B2, and CDE4. This actually might be the case that E is in total different cluster. Then we might have some other like variable that might be true. But then one can see that this variable that is 1 for T is clearly an extension of what was going on for S. Okay, so that is like that is kind of intuition there. Okay, and then one can argue that this is looks similar to our rounds of Sherali-Adams hierarchy of LP. Probably not in a very like precise sense, because like then I gotta define what the actual relaxation is. But then it's one can argue it's a variant of that. But then of course we added like some new constraints because it's like a correlation constraint problem. And then one can get some more intuition about these variables. Suppose that if your like variable, if your like set is like just one single variable, okay, so then YVT, it just means the probability that V belongs to a cluster of size T. Okay, so then one can say that okay, summation over T, YVT must be 1. Again, it corresponds to the constraint that each variable belongs to exactly 1 cluster. And then of course we were talking about the Xij variables that measure some distance between I and J. And then of course some Xij here, we can infer that from Y's. Okay, so if you look at the set of size 2, I and J, okay, so then basically YAJB, YA bar JB means the probability that I and J are in different clusters, and then I's cluster has a size A and J's cluster has a size B. Okay, so then if you sum them over all the sizes A and B, then this just means the probability that I and J are separated. Okay, and then crucially, because we did all the work of a preclustering, so then the way we use preclustering is the following. Okay, so we just hard code them into like our LP. Okay, so if we already decided that IJ are in the same cluster, so then we just like simply mean that Xij must be 0, which which will imply that every of these guys will be 0. And then if the IJs are E different, then it means that we're gonna we know that they're gonna be separate for sure. So then we just like we'll let the Xij to be 1. Okay, so that's the way that we are gonna use the preclustering. But then if you're like kind of a relaxation purist, then we needed this for our proof, but then it's not clear whether we have to do this hard coding to get a good algorithm. Okay, so it might be the case that you can start from actual relaxation that doesn't do any hard coding, and then you can still get a good approximation. Okay, so there's the hard coding. We did it for now, but then it's not clear that we actually need it. Yeah, but then I mean that's basically our like full relaxation modulo, some more constraints that we added. Okay, so yes. Okay, any questions about the relaxation? Okay, so that's a whole relaxation. And then yeah, let me at least briefly tell you how to finally solve the cluster LP solution. Okay, so then our idea is to round the previous actual LP to solve this the cluster LP. So yeah, then our job is to solve the cluster LP. But then actually our ideas are very simple. Okay, so then our rounding algorithm, algorithm to solve the cluster LP, is an iterative algorithm. So in each iteration, we're gonna sample like exactly one cluster, C1 through C capital T, where like T is the number of iterations. And then yeah, so okay, so each iteration we are only sampling one cluster at a time. But then the way we set up this rounding algorithm will be such that the probability of each vertex belonging to a cluster will be the same for every vertex. Okay, so then which means that if like the capital T is large enough, okay, so if you sample large enough clusters, then each vertex will be approximately contain the same number of clusters. Okay, so suppose that each vertex is contained in approximately L clusters. Okay, so then my final cluster of the solution is just like, okay, let's add the indicator vectors of all the clusters that we sampled so far, and let's divide by L. Okay, that's exactly like our cluster LP solution. Because if you remember the cluster LP, the only meaningful constraint was that each vertex belongs to exactly one cluster. Okay, so yeah, in this case, if each vertex belongs to L sample clusters, then by dividing by L, we are ensuring that each vertex is belonging to like fractionally one cluster. Okay, so that's the whole idea. So yeah, then all I need to describe you is how to sample one cluster in one iteration. So all the clusters are independent from each other. Okay, so then now we are gonna use this the fancy tool that I wanted to use for max CSV. Okay, so first we're gonna sample cluster size S prime and some pivot vertex P. Okay, so of course, like if we had the optimal distribution of optimal solutions, so then the ideal distribution for S prime and P will be just like, okay, let's if you have an optimal solution, then let's sample like one optimal cluster C, and then sample like one random vertex P there, and then output the size of that cluster and the random vertex P. So that's our like ideal distribution. Of course, we don't have the distribution of optimal solutions, but then at least that kind of marginal information can be deduced from our variables. But then if you have S prime and P, okay, so then remaining goal is to decide, okay, so who are the vertices that will be the same cluster as our pivot vertex P? Okay, that's the only remaining decision, to sample like a one cluster. And then actually for me, I think initial eureka moment was that, okay, so now this problem is just like 0-1 decision for each vertex. It's now like we sample P, we even know the size of the cluster. Okay, so then yeah, all you're doing is decide each vertex it's gonna go with P or not. Okay, it's a 0-1 decision for each vertex. Okay, now it's like the Boolean CSV problem. Okay, so then yeah, if you know this, then one can kind of use like the variance reduction rounding, almost as a black box, to sample like one set of vertices C. Okay, and then yeah, once you do this, then actually one can prove this like the nice claims saying that, okay, so because of the way that we set up this previous relaxation, the probability that each vertex will belong to the sample cluster will be exactly the same for every vertex, which is crucial in this part. And then probably more importantly, even the pairwise the error, correlation error, can be charged to the number of the question marks there. Because like if you do this, then actually we're only gonna use this rounding for the part that was question mark. Because like if for the things that were not question marks, we already know that it's exactly 0 or exactly 1. So there's like nothing to decide. Okay, for at least we came up with a scheme such that for the rounding error, if it's already 0 or 1, then we don't need to pay the rounding errors. Okay, so at least yeah, we can claim this is true, and then at least the amount of error is epsilon times the number of question marks. But then we argue that number of question marks is at most like the constant times the optimal value. Okay, so then by reducing epsilon to be arbitrary small constant, then yeah, one can see that the total error that we incur is also like very small compared to the optimal value of the instance. Okay, so that was yeah, it was like kind of technical, but then at least like that's the high level of what we are doing. Good. Okay, so that's how we solve this LP. But I think the good news is that the second part is like completely independent. And then if you're only interested in improving approximation ratio, then you only need to like listen to this part, because like that part is a completely black box. Okay, so yeah, and then second part is like arguably easier, at least until like 1.5 approximation. So let me tell you why. And then our rounding algorithm has like it's a combination of two algorithms. Basically, we run two algorithms and then take the best. And then these two rounding algorithms are called the cluster rounding and the pivot rounding. And then actually the rounding algorithms themselves are like extremely simple. So let me tell you what they are. Okay, so the first guy, cluster rounding. Okay, yeah, actually that's the entire description algorithm, even in the paper. I just copied and pasted it from the paper, which is basically 2 lines. Okay, so what we do here is that again this algorithm is an iterative algorithm. Okay, so we are constructing one cluster at a time. And then in each iteration, okay, so we want to sample one cluster, but then the cluster LP is exactly giving you like some information about this, because like a cluster LP has like one variable for each cluster, and then this sub S is corresponding to the probability that that guy is a cluster. Okay, so then what are you gonna do? Okay, so then yeah, we are just like sampling S with probability proportional to ZS. That's the entire algorithm. Of course, yeah, first iteration it's fine, but then from the second iteration, just like it might be the case that there are like some overlaps. But then we handle overlaps in the most obvious way, just like yeah, whenever like you occupy some cluster, make it a cluster, move from the remaining graph, the current graph, and then continue the clustering only with the remainder of the instance. Okay, though yeah, you don't need to resolve LP. Okay, so we are using the same S probabilities. But then after solving S, new cluster is only the intersection between the remaining part and the S samples. Okay, so that algorithm is like extremely simple. That's it. And then for this rounding out, the analysis like is very simple as well. Okay, suppose that yeah, let's look at this edge U and B. Okay, and then yeah, let me explain this picture. Okay, so the height corresponds to the probability space. So you can think of this as the height 1 bar. Okay, and then of course, if you remember cluster LP, then it has like the variables for the sets. Okay, so S1 is like some set that has that much value in the cluster LP, and then S1 is like the both U and B. Okay, so that's S1, and the same as like S2, S3, S4, S5. Okay, so those like 5 sets are the sets appearing in the cluster LP that contain both U and B. That's good. And then S6 is a set that only contains U, not V. And then S7 is the guy that only contains V, not U, and some other variables. Okay, then yeah, one can say, okay, so for V, the summation of Z values of S1, S2, S3, S4, S5, S7, it must be 1. And then for U, I think the summation of these guys must be 1. Okay, so that's the interpretation of the picture here. And then one can recall that, okay, so then the XUV, the probability that U and V are separate, should be exactly the probability of S7 or the probability of S6. Because like if S7 is a cluster, then the U and V are separated, or if S4 is a cluster, then the U and V are like together. Okay, so that's the interpretation of this picture. Okay, any questions about this picture? Okay, so then yeah, once you see this picture, then actually the analysis is just a follows, because of course this rounding, we sample many sets, and then yeah, after sampling, it's gonna remove them from the current graph and then proceed. But then for the purpose of U and V, we only need to worry about those 7 sets, because all the other sets like don't even touch U or V. like whatever they do, I don't care. So U and V state is decided when one of these 7 sets is sampled. But then, yeah, all we are doing is like the sampling sets from according to probability of Z values. Then basically our whole game is, okay, so given these 7 sets, who's going to be sampled first? And then of course, like, yeah, the first sample sets will be decided according to the probability of here. Okay, so then the probability that U, V is separated is exactly when the probability of S6 or S7 is a sample. Okay, so these guys have the XUV probability each. So one can see that the probability of as UV separated is like 2 XUV divided by the total probability of these sets, which is like 1 plus XUV. And then similarly, of the probability that UV are together, it's just like summation of this red probability, which is 1 minus XUV divided by 1 plus XUV. And then if you compare those the probabilities to their contribution to the LP objective, then yeah, one can see that actually plus edges will get 2 approximation, and then the minus edges will get actually better than 1 approximation somehow. Yeah, at least that's yeah, that's the whole analysis, which is a 2 approximation. Okay, that's good. But then the second rounding algorithm is slightly more complicated. Okay, so it's a called pivot, but then again, it's not too complicated. It's just like it's a whole algorithm from the paper again. Okay, so it's again like iterative algorithm. Yes. So in the worst case, you get 2 approximation. It's if XU is like very small, close to 0, then you're gonna get 2 approximation for that edge. Yeah, that guy already is like 2 approximation. Yeah, at least yeah. I mean that's yeah. We will balance it with the second rounding algorithm. Then within this, like we couldn't find a way, or there might be some way. Yeah, yeah. Yeah. So the second algorithm is similar in framework. Okay, so yeah, the iterative algorithm, we are constructing one cluster at a time, and then the way we construct a cluster is to sample like one pivot vertex U, and then again decide who's gonna go with U. And then here, like it's I don't have a great intuition about it. I think it's a kind of outcome of fine engineering. But then the way we did it is that we divided all the other vertices into 3 groups, depending on their relationships to U. Okay, so the first group is like the plus neighbors of U that are like close in the LP value sense. Okay, so them you're gonna take it, all of them. They're gonna go with U. And then all the minus neighbors of U, we will sample them independently according to their distance of U, because they're totally independent. And then only in the middle group. Okay, so yeah, still we want to use the power of a cluster LP that can sample from the set of sets. Okay, only from the middle group here. So we're gonna, again, as usual, we're gonna sample the set S among the sets contained in U, according to the probabilities given by the cluster LP. And then we're gonna take an intersection of that set S and the middle part. Okay, so all these red vertices are the vertices that we're gonna take. Okay, all of the left part, the right parts are rounded independently, and then the middle part is rounded in a correlated way. Okay, so again, I don't have a very good intuition about it, but then this is what we do, and this is what we get, where we get some improvements in approximation factors. But then of course we gotta analyze it, and then here, if you know this like the classical pivot algorithm or like pivot rounding, then yeah, we are basically the same analysis framework of this work by Alantha Newman, which is like triangle analysis. So let me briefly tell you how we do it. Okay, so suppose that let alg be the number of wrong edges. Okay, so then in each iteration, so our algorithm we just sample one cluster S and then remove it from the graph. Okay, so then yeah, one can say that edge UV is going to be removed if like U or both B is removed from the easy nets. We remove one of these guys, and then among some of the removed edges, some of the edges will become wrong, in a sense that if like UV is a plus, but then exactly one of them is a new cluster S, then we know that this guy is violated. Or like if UV is a minus, but then you remove like both of them together, then you know that, okay, so then you're violating that edge as well. Okay, so then in iteration T, if you let the alg sub T to be the number of edges becoming wrong in the iteration T, and then LP sub T to be the total LP values of removed edges. Okay, so then yeah, one can see that total alg value that we pay is a summation of all these alg values across different iterations, and then the same as LP value. Okay, so initially LP was containing this value, and then each iteration the LP is decreasing by some factor. Okay, so and then if you can say that at least in expectation the alg t is at most alpha times LPT, then at least intuitively we're gonna get an alpha approximation. Okay, which is good. Then you can focus on only one iteration. That is good news. And then this is our goal. But then of course, there's still the alg and LPT are like complicated quantities. But then of course, if you look at the definition here, then alg expected value of alg sub t can be decomposed as this summation 1 over n times the summation over like the tripled PUV, where like the P denotes a random pivot, and then UV is like the one edge that we are analyzing. Of alg sub PUV, where like alg sub PUV is exactly the probability that UV becomes wrong when P is pivot. Okay, so this is just expanding out the definition. And then similar for the LP value. Okay, so then it's good. Okay, so then we each of the expected values are summations of n cube guys, and then at this point it's tempted to try like term by term analysis. Each term left is at most alpha times each term on light. That's not true, but then like the brilliance of just triangle analysis is to show that okay, let's group these like the terms as a triangle. Okay, so we know that like just term by term analysis is not going to work, but then you just group them in this way. Say like alg PUV is a summation of alg sub PUV plus alg sub UPV and alg sub VUP, and then do the same thing for LP. Then somehow magically the one can prove a bound of approximation ratio alpha for some constant alpha. Okay, so of course, yeah, for any possible triangle PUV. And then of course, yeah, and then one can say proving this shouldn't be of too much of a problem, because yeah, we are only looking at one triangle PUV, and then triangles are determined by their signs and their LP values. Okay, so it's just a constant variable claim. So of course, it's a kind of technical to prove it, but in principle, we can prove. Okay, so of course, yeah, in reality, we use a different approximation ratios for plus and minus edges, because in previous algorithm had that property as well. And then if you're combining with the previous rounding algorithm, then that part gives you like 1.5 approximation. Actually, so yeah, until here, like I think if you start from cluster LP, then it's only like 5 pages or like 4 pages of total analysis, which is not too bad. Okay, and then but then like slightly more complicated thing happens when you like try to squeeze beyond 1.5. Then we gotta search over like global triangle distribution, meaning that so this claim we want this claim to hold every triangle. Okay, and then of course like there must be some triangle where this analysis is tight, the alpha is tight. Okay, so then yeah, perhaps okay, so then if you just want to use this claim, then you cannot go above alpha. But then whatever the worst case triangle is for this claim, it might not be the case that actually the instance cannot have only these triangles. Okay, so okay, and then that's exactly the property that we are exploiting here. Okay, so let's yeah, see one example. Somehow in all this our work and even previous work, if you do this triangle analysis, then for some reason there's always like this bad triangle. Bad triangles always looks like this. It's a triangle IJK, where like the one edge KI is 1. So K and I will be always separated. And then I and J and then J, K have a distance 1/2. Okay, so somehow that's always like the bad triangle. Okay, then the question is like, okay, so then can every triangle be bad? In our LP relaxation. Yeah, that's a question. If that's not, then perhaps we can do something slightly more. And then perhaps one special version of this question is that suppose that let's look at one vertex J. Okay, so can every triangle involving J be a bad triangle, where J is the anchor triangle, anchor vertex, like adjacent on the two half edges. So that's exactly the situation. Okay, so yeah, it means that J is the anchor of this like the 3 bad triangles, JAB, JCB, JAC, and then the ABC have a distance 1 from each other, which means that A and B and C are always separated. But then the J has a distance only half to like all ABC. Okay, so yeah, do you find this thing kind of suspicious? A and B and C are always separated, but then somehow J has to be with A with probably half, with B probably half, and C probably half. I think I see like some faces like just think it's nonsense, and then it doesn't make sense because like A and B and C are always separated, but then how come like J with A with probably half, B with probably half, like C with probably half? If there was a 1/3, 1/3, 1/3, then probably I get but then 1/2, 1/2, 1/2 doesn't make sense. And then like fancier way to look at it is some kind of matrix, okay, like A sub ij, A j I k being the probability that these like j I k in the same cluster, in the cluster LP. Okay, so this kind of matrix, one can easily see that this guy is a PSC matrix because like this is a moment matrix of some set. So at least like that's one thing one can infer from this type of situation. Okay, so if you are looking at the cluster LP, then you cannot have like this type of configuration. Okay, so it cannot be the case that J is the anchor of like numerous bad triangles. And then similarly, we observe like one more PSC constraint that makes sense, something like this. And then the final like analysis is actually done by designing factorializing LP and then computation is solving it. Okay, so formally we say that triangle type is just triple over 3 discretized Xij values. Let T be the set of all the triangle types. Okay, then the question we are asking is that, okay, suppose that we are having some probability distribution P, probability P. Okay, so then the question is that, is this triangle distribution realizable for any instance that can arise from our like cluster LP? Okay, so so I don't know, we don't know how to do it exactly. Okay, so I think this exactly deciding this problem is a really hard problem. But then at least I told you that we can put some STP constraints on this the P. Okay, so then our like final analysis is to certify that for any P feasible for that STP, which is like necessary condition for actually being realized as an instance. So then now once you have P, then you have a whole distribution of triangles. Okay, so then you can do some kind of average triangle analysis because like if you think about previous claim, then each triangle will have a different approximation ratios. And then it may not be the case that worst case triangle will always be the case. And then if you combine it the cluster rounding, and then it yields like 1.437 approximation. Okay, so that's how we got it. I mean, good thing is that at least our STP is supposed to give an upper bound. Okay, so if you believe our primal solution is correct, then I think it's I think fine mathematical proof. That's it. And then let me quickly tell you some directions about correlation clustering. Okay, so of course the first problem is okay, what's the true number? Okay, so the upper bound is 1.43, and then lower bound is like 24 over 23. And then as I told you, like 4/3 is a barrier, at least a first barrier. And then exactly the reason that 4/3 is a barrier is that the 4/3 is the integrality gap of the cluster LP. Okay, so that thing was extremely powerful, but then even that guy is a gap of 4/3. So then obvious question is like, can we match this 4/3? Okay, so that's a nice open question. But then as I told you, even we don't know how to match the integrality gap of standard LP, 2.06 versus 2. Okay, so I think yes, that's why I think the matching the integrality gap of the standard LP will be useful for like pushing this number all the way down to 4/3. Okay, that's one nice question. But then of course, but then there's a gap between 4/3 and 24 over 23. So then one can ask, okay, what's the how are we going to explain this the gap between 4/3 and MPRness? Okay, so in some sense, so our like MPRness like 24 over 23 is based on the gap for the cluster STP. Okay, so I'm not going to define it, but then one can kind of imagine like instead of giving like one number to a set, we can think about one vector to a set. So we're going to get 2 to the n vectors doing their own things. And then, so basically, if you give me a gap instance for cluster LP, then I think there's a decent chance of converting that to NPR. then yeah, one can expect that, okay, so then what's is that guy the right relaxation for the problem? But then one issue is that actually we don't even know, I don't even know how to like solve the cluster LP, a cluster STP. Okay, so LP, we were able to solve it, but then yeah, we don't know how to solve cluster STP. So it's not even clear whether like this is a polynomial-time algorithm or not. But then on the flip side, I think can we actually prove that cluster STP is as strong as all the polynomial-time algorithms? Okay, so that's yeah, both are like nice questions. And then the final question, if you care about running time, especially in this gigantic exponent, then is this running time necessary? And then actually there's like another work that gives 1.8 something approximation in the FPT time, in the sense that running time is a sum function of epsilon times linear time. It only depends on the linearly on the number of plus edges. Okay, so it's a really good running time when epsilon is a constant. So they get that. And then they are based on like very purely combinatorial technique based on local search and random sampling. Okay, so there might be some separation between the algorithms whose running time has like one epsilon in it, or like purely it's FPT running time. Clear is currently the gap is 1.4 versus 1.8, but then I don't know whether it's this gap will be somewhere inherent or like every approximation algorithm will be made near linear. I don't know. Okay, so I think these are like yeah, let me just skip this part, and then that's it. Thank you. Yeah, dual of the cluster LP, right? Yeah, I think it's a some version of a sparse cut. I don't exactly remember. Yeah. Yeah, so yeah. So it's I think in general instance it's gonna be like hard to solve, even approximately. But then since we are dealing with the complete graph, it might be the case that actually even dual LP might have like a very good approximation algorithm. Though that's not the direction we pursued. I think, yeah. Yes, yes. Yeah, there might be something known. I think, yeah, then I am not aware of, yeah, but then it's a highly likely that somebody studied this. Mhm. Yeah, general graphs, I think, yeah, general graphs, I think. Yeah, because like if you can solve this cluster LP, then you're gonna get at least the two approximation for free by the first rounding algorithm. Yeah, yeah, even for non-complicated, because it goes like the edge by edge analysis. Yeah, exactly. That's exactly the approach we took the second version, yeah, of the paper. I think, yeah, we didn't even, I mean, yeah, we didn't even write down the cluster LP. So we started from basically the initial LP that we started with. And then for some reason, yeah, we actually did the rounder cut. And then yeah, in some sense, actually the cluster LP is kind of redundant. Because like, yeah, if you can remember like the algorithm to solve cluster LP, there's like the iterative sampling of cluster. That's like that's almost same as like the first cluster rounding algorithm, just like sampling one set. So yeah, so definitely yeah, so rounder cut we did it, but then somehow I think in this version we thought that the cluster LP is kind of nice intermediate LP that oh
Yeah. I think yeah. I think that's pretty much what we did in the second version. Yeah. Though I think we thought like rounder code is like more complicated than good. Yes. So yeah, it's known that if k is a constant, I think so there is p-test whose running time is exponential in k. I think it's 2 to the k times the polynomial in n. Good question. So I think so if you're naively asking, okay, what happens like dense graphs or expanders, there's like kind of easy, like very stupid way to like just take a general instance and then encode it as like expander or like dense instance. Because like what I can do, okay, suppose that this is the actual instance. Okay, so then I can just like I can embody them as like gigantic instance, and they think okay they are like all the minor sets. Okay, so and then of course you can put as much as you want to ensure that the whole graph is like on the surface is like expander, dense graph, whatever you want. But then of course it's kind of stupid because like then of course you're only solving this guy. But then of course if you want to correlate this structure with the plus and minuses, then perhaps you might be able to say some interesting things. But then if you're just like if you're just doing this, then of course like this stupid example will let you embed the hard instance in a dense instance.